Good afternoon. We begin today. We continue with our session on Six Sigma, and the particular topic that I'll be discussing today. There are 3 lectures to be given today. These cover the area of acceptance sampling. This is one area where basically the process that you're trying to utilize is how to sentence a lot. Let's say you are a supplier and you have supplied a truckload of items to a particular company, and this factory has received your goods. Now they have to decide whether to inspect all the items that are on the truck, or should they just take a sample out of that truck, and on the basis of that decide whether to accept the truck for their production, or they should reject it and return it to you. This is to be based on a sample that is drawn from that truck. The idea of acceptance sampling came along when it was realized that many times goods are received in large lots, and it's almost impossible to inspect each and every part that is part of the lot. That is actually generally not possible. So if you look at, for example, I have here in the slides, I've got a bunch of bottles, and these bottles have been figured out. They have been filled with some liquid, and we want to make sure that there is enough liquid that is within the specification that has been given out for the amount of liquid to be there in these bottles, in a manner, in such a way that we are able to accept the lot. There is sufficient amount of liquid in each of these bottles on an average basis. Now, if some particular bottle turns out to be containing less liquid, it will be the process of filling the liquid in these bottles is going to be then a defective one, and the lot itself also will be a defective lot. So in fact, what we will be trying to do is, we have this large lot that has been supplied to us, and instead of inspecting each and every bottle that is here, we'll probably take a few samples out of this, and on the basis of inspecting the quantity of liquid in that bottle, in those bottles, within the sample, we'll decide whether to accept the lot or to reject it. This procedure actually was created around World War II, when the military became the largest consumer of any kind of goods that was supplied to the military. Civilians certainly did not consume as many things, but the military in large quantity, they obtained various types of supplies, and they wanted to make sure they had a procedure in their place so that they could just basically order a lot, but inspect only a part of that lot, which would be called the sample. And on the basis of the fate of that sample, they would decide whether to accept the lot or to reject the lot back to the supplier. This procedure, by the way, because it does not inspect all the items, it cannot guarantee 0 defects. There will be a few items that might sneak in because you are really not inspecting all the items. Each and every one of them you are not inspecting. Therefore, this procedure, the acceptance sampling procedure, is not consistent with the objective of 0 defect. That's something we've got to remember. Also, the other thing we have to remember is acceptance sampling. This procedure that we are using does not actually give us much idea about the filling process, about the production process. It does not do that. It basically talks about the quality of that lot, the overall quality of the lot itself, and that's it. It says nothing about, it will give you no hint as to what is the quality of the supplies that you are receiving on an overall basis, and what is the production process is like. That also you'll have no idea about, because you are doing it on the basis of just a few samples that you draw out of a particular lot. This sample that you draw, it has to be a random sample. It cannot be a sample that is selected by looking at, for example, the bottles that are nearest to you or the parts that are easy to get from that full lot. It's not to be done that way. And also it's a process, it's a procedure that will decide sentencing the lots. These are incoming lots. They are arriving perhaps by trucks, or they may arrive in large boxes of transistors, or boxes of certain electric bulbs or something like that, or it could even be boxes of these pencils, containing these pencils. We're not going to inspect all of them. We're just going to take a few samples. So we'll take a few samples out of them, and on the basis of inspecting this sample, we'll decide whether to accept that full lot that I have or to reject the lot. That's what the idea is. One of the most widely used sampling plans is provided by the military, and that is called the MIL STD 105E. That is a sampling plan that is utilized by the military, and it basically talks about talks about sampling the lot, and then on the basis of some rules which are provided by the MIL-STD 105E plan, sentence the lot to be acceptable or not acceptable. What exactly is this business of acceptance sampling? The purposes are twofold. First of all, we determine the quality level of an incoming shipment. This is what we try to do by doing acceptance sampling. And also we try to determine whether the quality level of the parts that have been supplied in the lot, whether it is within an acceptable level, acceptable quality level. And again, like I told you earlier, it is not really possible for me to make any statement about the process that is producing those items. That is not the objective of acceptance sampling. Now, acceptance sampling, if you really look at what is this, it's a statistical procedure. It's another area of quality control and quality improvement. It's closely connected with inspection and services and testing services. An inspection can actually occur at many points in the process. For example, when you've got incoming parts, when you've got parts which are just arriving from a supplier, you could inspect it before it enters your shop. And after you've done your production, then perhaps when you're making your shipments, then again at that point you could do your inspection to make sure that the parts that you supply to your customer, those are of acceptable quality. So in fact, two places you could do inspection, you could do acceptance sampling. One is when the parts are received, and the second point where you could also do your inspection and apply the acceptance sampling principles is after production, to make sure what you ship out is within the acceptable quality level. There are various types of acceptance sampling plans available, and broadly speaking, there are three types of plans that are utilized. One is called the single sampling plan. The second one is double sampling. Then you've got multiple sampling or sequential sampling. And I should just tell you that all of this is based on inspection of the limited amount of products that you pick up. So from the lot, I just picked up a small sample. And on the basis of the results of inspecting this small sample here, I'll decide the fate of the full part, the full lot that has been supplied to me. So really it depends on the performance or the quality level of these two parts or the three parts that are in the sample. I'm going to be deciding the fate of the full lot based on the performance of these two sample items. That's what I'm going to be doing. There are now a couple of types of approaches to this. One is to look at the attribute of a particular item, and this is like a quality attribute that can be classified as acceptable or not acceptable. For example, a pen may write or it may not be able to write. So it's good or bad. That's an attribute. Writing quality, writing performance is an attribute which can be sorted between good and bad. So in fact, that's like one way to try to do your inspection. The other way is to look at the dimension, or for example, look at some quantity that can measure. As far as this particular pen is concerned, there will be certain items here, certain characteristics that I should be able to measure, such as dimensions, such as viscosity and so on and so forth. Many of these characteristics, they can be measured. These are different now from attributes. Attributes are either good or bad, and whereas a quality characteristic that can be measured on a scale, that is a variable. Sampling plans can be used both to check quality when the quality characteristic is an attribute, and also sampling plans can be applied in situations when the quality characteristic is a variable quantity. The approaches are different. The two approaches, they are different, but essentially in all of these cases, you are looking at a full lot, and from that you have picked up a few samples, and based on the performance of these samples, you are then going to decide whether to accept the full lot or to reject it back to the supplier. There is another fate, of course, that the rejected lots can be subjected to. Suppose you have rejected a particular lot. It's very possible that you might like to carry on with your own production. You are the user of these parts. It's very possible you'd like to carry on with your production. What you'd like to do is, you look at the full lot now. This lot is now the candidate for rejection. So I've got this part. These parts, and then they make this lot, this full lot. And this lot, of course, is such that some of these are defective, some of these are okay. What I'd like to do is, I'd like to continue using these parts. I'd like to continue using these parts. Now, obviously, I cannot use the defective parts. I cannot really use a defective part and put that in my production. I cannot do that. So, one way to tackle this lot that has been, let's say, rejected is to remove the defective part and substitute that with a good part. If I do that, I still have a handful of usable parts. And these are the parts that I could put into my production and carry on with my production. I'm the user. So now this determines one disposition of the part. Or the alternative is, you reject the whole lot and let the supplier figure out what to do with the defective part. So now if I decide that yes, okay, there is a lot that is to be rejected, I can then inspect the lot 100% and remove all the defective items from it and substitute for them good parts. If I do that, then of course I end up with a handful of good parts with me. That's the lot that has been rectified. The defective parts have been removed from it. This lot I can then put into my production. I can carry on with my production. And this mode of acceptance sampling is called rectifying sampling. I've rectified the defect, I've removed the defect, and I've substituted that with a good defect. Now this has good part. Now this of course requires me to have a handful of good parts with me. I should have these in reserve, just in case I find a few defective parts in the lot. I should be able to remove that defective part, and I should be able to reserve from my reserve, draw these good parts and put them in place of the defective items and carry on with production. That is something I should be able to do. Attributes, as I mentioned to you, attributes are measured on a go-no-go basis. They are judged on a go-no-go basis. And variables, actually, they can be measured on a dimension. So for example, I could have a measurement device, and on that measurement device, I could on the scale, I could measure the quality characteristics. If it's dimension, I can certainly apply the scale there, and I can actually find out what is the right length. Is the length right? Is the length okay? If it is not okay, of course, then of course I do that. So what I'm doing is, I'm measuring the characteristic, which in this case turns out to be the length of the bar that I have there, the length of the bar, and I measure that using my scale. In this case, I've got a variable characteristic, and I'm measuring with a measuring device. This can also be done during inspection. In fact, this is like one way to inspect a variable characteristic. A variable characteristic, here is the dimension of the part. That can be measured with a particular gauge. That could be done. So there are two ways now to evaluate characteristics. One is to apply a go-no-go gauge. And this is how I evaluate attributes, which are basically, they can be classified into an acceptable quality level or a rejectable quality level. And this is done on a go-no-go basis. On the other hand, I could also have dimensions, and those dimensions can be measured using a scale. And then I could really have a variable characteristic that can be measured by using a gauge. The scale here is a gauge that can measure that attribute. Why don't we use 100% inspection? Why do we have to draw a sample and so on and so forth? Well, there are a couple of reasons. One reason is, if you try to do 100% inspection, you're going to be inspecting a whole lot of items. And there are a couple of things that can go wrong. If you actually try to inspect all the items, A, it is going to cost you a lot of money. And B, it's also very possible that you'll make some mistakes. If you're trying to do 100% inspection, you might make some mistakes in inspection itself. So in fact, these are a couple of reasons why one should not try to attempt 100% inspection, except for critical characteristics. Like for example, if there's an electrical component, if there's some chance of this guy having a critical defect, if it can give a shock to the user, then of course I've got to inspect 100% of these items. So unless the characteristic is critical, I can generally do what we call inspection on a selected basis, based on a sample. That we could do quite easily. It's also possible that when I do my inspection, I am not able to really decide whether to accept the lot or to reject the lot if I have no basis to compare that quality to something. So you got to have benchmark quality levels. What am I talking about? I have here some terms which are used in sampling. For example, there is something called AQL, which is the acceptable quality level. Acceptable quality level is that level of quality that I am willing to live with. I as a user, it's generally expressed in percent level. And generally speaking, AQL, the quality level of a lot which is at AQL level, it is all right for me to bring this into my shop and to start using those parts which are at the AQL level on the average basis. But then it's very possible that the lot that I receive is at this level, which is the RQL level, rejection quality level. Now this is the distinction between the two, which is AQL and RQL, is the following. A lot quality which is at AQL level is good enough for me to carry on with my routine production. Yes, there will be a few defectives there, but I'm willing to live with that because I'm not doing 100% inspection and I'm really banking everything on the basis of the acceptance sampling plan that I put in place. And I'm going to be going along with that. Yes, I do end up with a few defective parts in my production, but I remove them or I do some rectification and so on and so forth, and I live with them. On the other hand, RQL level, the rejection quality level, is a defect level, an overall defect level in the lot, which is not acceptable to me at all. In fact, it may be very possible that if I receive a lot which is at RQL level, my production system is going to be interrupted very often, very frequently. And that means I'll have production downtime. Now, what have I gained here? I've really gained not much. I've really lost a lot. I'm going to be losing some real production time because I've got a whole bunch of defective parts in the lot that I've received. So generally speaking, what users would like to do is they'd like to receive parts, as many lots as possible, at the AQL level. And they should try to reject as many lots as possible that arrive at the RQL level. In between, of course, there is something that is called the probability of acceptance, and we're going to be looking into this as we go into our further down in this study there. Let's take a look at a couple of other things. One is, suppose my parts have been received, suppose my lot has been received at the RQL level, which is also called LTPD, lot tolerance percent defective. Now this is certainly the rejection quality level. This is the RQL level. Now because I'm not doing 100% inspection, I'm inspecting just a few parts out of the full lot that has been submitted. All I'm inspecting is just a handful of items. I'm just inspecting a small sample that has been drawn out of the full lot. I'm taking some risk. The risk to the consumer, the user, is that a few parts, even if the sample looks okay, when I look at the full lot, it's very possible that the full lot might contain a few more defectives, which will then sneak in because I'm sentencing the lot. I'm sentencing the fate of the lot based on the results of inspecting just a few items. Now, this is something that's actually exposing me to some kind of risk, and this risk is called the consumer's risk. I'm the consumer. I expose myself to this risk the moment I do sampling. I expose myself to be accepting some lots which are really not quite at AQL level, but they are worse. They have worse quality level. That's actually a consumer's loss. Now, because I'm doing sampling again, and I decide the fate of the lot based on just a few handful of items, and these are in the sample, it's very possible that this particular sample ends up having more than its proportionate share of defective items. It's very possible. So like here I've got 5 items and one of them turns out to be defective. If there's one defective out of 5 items, that's a pretty high level of defectives. But this could just be due to a chance. Now what will I do? My sampling rule is going to tell me the moment you find one defective item in 5 that you've sampled, reject the full lot. Now the overall quality of the lot may be pretty good, but by chance I ended up with this one defective item in my sample. And that's actually pretty bad news for the supplier, because the supplier says, well, I understand you're not doing 100% inspection, But the way you've set up your sampling plan, sometimes you end up looking at, perhaps by chance, defective items in the lot that you have, in the sample that you have, and it reject my lot. My lot otherwise has good quality. But because of your sampling procedure, I, the supplier, or I, the producer of those parts, I end up getting subjected to some risk. And this is actually the producer's risk, or basically the supplier's risk. So there are two types of risks here involved. As I show on the slide here, there is the consumer's risk, which is like the probability that the lot containing defectives exceed the rejection quality level. And still it turns out that I end up accepting this lot. It's very possible. On the other hand, there is this other types of risk called the other type of risk called the producer's risk. This is the probability that the lot containing an acceptable quality level will be rejected. Now these two risks are there because I'm not inspecting everything. These two rejects are there because I'm not doing 100% inspection. If I did 100% inspection, I'll know the exact quality. I would know the exact quality of that lot. And therefore, there's no question of any kind of risk being subjected to one party or the other. Why not do 100% inspection? If we know all this, why don't we do 100% inspection? Couple of reasons are there. One is, generally speaking, 100% inspection will mean, for example, here if I received all these pens, and these have arrived in a lot, and all these pens they have arrived, and they could be like, a box could contain 200 such pens. They've been brought in for the office, and I've got all of them in a box. If I do 100% inspection, I'll have to inspect each of those pens. That's a lot of inspection. That's a lot of time spent on inspecting only. So that's like one reason why this kind of deal, which is like 100% inspection, it may turn out to be something that is rather expensive. It's also very possible that in the process of inspecting, I destroy the product. Many times, if you're trying to inspect something, you end up destroying the product. If you're trying to detect the strength of this, for example, you may destroy it. And that means you're losing one good part, one decent part which was otherwise quite usable. You're going to be losing that. So this is also one other reason why you should not do 100% inspection. Then when inspectors are handling these things, they may induce some new defects. It's also very possible that if you're trying to inspect something, your process of inspecting itself may make the item, may render the item defective. That's also possible. And also it's a very tedious job. So if I've got all these items to inspect, I've got a couple of hours and I've got all these different items and I must inspect all of them. My God, that's a pretty tedious job. So it's very possible I may go a little slack if I have to inspect a lot of items. So if I'm going to be using the 100% inspection scheme, my job may become very tedious. I may get tired. I may make errors and so on and so forth. These are the different reasons why doing 100% inspection is not the way we should be doing our inspection. Let's take a look at the mechanics of lot by lot inspection sampling. I have the lot, which is this yellow box here. That is the lot that I have received. I draw out of this n items, and this little n items is basically my sample. My sampling plan tells me to pick n items and inspect them all. So the sample itself is 100% inspected. So out of the big lot, which comprised big n items, I pick small n items, I inspect them all. And then there's a control number, there's C. C is a control number. If the number of defectives in these n items exceeds C, I will reject this lot. And if the number of defectives in this sample here, if it goes only up to C but no more, I will accept the lot. And then of course, the moment I have my sample with me, I'll count the number of conforming items which are like good items, and on the basis of how many items I find to be defective, I will either accept the lot or reject the lot. So again, to go over the procedure again, I've received the full lot, which is of size n. I draw a sample of n items out of it. I have a little rule here which says if the number of defective items which are found by 100% inspection of the sample, if that number of defects, if it exceeds C, I'll reject the lot. Otherwise, I will accept the lot. That is the sampling screen there. So, in fact, that is what is written out here in the statement that is down below here. Specify the plan. For a lot of size n, find little n, which is the size of your sample. Find the acceptance number or the control number, which is C. Do 100% inspection of the sample and reject the lot, reject this full lot if the number of defects found in the sample exceeds C. Otherwise, accept the lot. This is the process that will be repeated over and over every time a lot of size n is submitted. Now again, to basically define these quantities there, AQL is the acceptance quality level. It is the smallest percent of defectives that will make the lot definitely acceptable. I can live with in the long term, I can live with the AQL level of defects in the lot, that I could do that. So basically, this is the baseline requirement for the customer, for the user. Now RQL is, which is also called lot tolerance percent defective, or LTPD. This is the quality level that is unacceptable to the customer. Even if one lot arrives and it passes inspection, passes the acceptance sampling process, and it gets into the customer's shop, that's going to be bad news. It's going to cause perhaps a lot of production interruptions and so on and so forth. This is not something that the customer is willing to live with. So in fact, what we have to remember now is that I'm sentencing the lot. Sentencing basically says decide to accept it or to reject the lot, return it to the supplier based on whatever I see in the sample. The two risks which are involved here, because I'm not doing 100% inspection, I'm basing my decisions based on samples only, the samples that I draw, and they are of size little n. A good lot may be rejected, that's also possible, that's very possible, and also a bad product lot may be accepted. These are the two types of risks which are there. A good lot may be rejected, which is still only at AQL level of defects, and a bad lot which is generally at near the RQL level, it may be accepted. And these two risks are there because I'm not doing 100% inspection. I'm banking on the basically the items that have come in the sample that I've got. On the basis of the quality of the sample that I pick from that big lot there, I'm deciding the fate of that big lot that is there, either to accept it or to reject it. Now, where do I use acceptance sampling? I show a few processes here. The first process is I've got the production process, then I do inspection. At this stage, I could do acceptance sampling. This is called outgoing inspection. And whatever lots pass the outgoing inspection, those are shipped to the customer. This is like one particular process. Then I process the products, process the items, and I ship them to my customer. And before the customer accepts it, he does an inspection, and this is called receiving or incoming inspection. That's what the customer is doing. My shipment took place here, and the lot has arrived at the customer's doorstep. He does this inspection by using some acceptance sampling plan. Then of course there is the third process procedure which is available. I supply the parts and the customer does inspection by applying some sort of acceptance sampling plan. He accepts certain lots which he uses up, but he rejects also. It's very possible he will reject certain lots. The rejected lots can either be scrapped or they may be reworked, or they may rectify that particular lot and accept it. So these are the different approaches, these are the various uses of the acceptance sampling which are used by industry. What are the different methods I could use? I could start with something that is called single sampling, which really basically says, as it shows on the slide here, I draw just one sample. I just draw one sample out of the lot, and based on the inspection of that one sample, I either reject the lot or I accept the lot. Or what I could do is, I could draw one sample, do some inspection, and perhaps I cannot decide whether to accept the lot or to reject the lot. And in that case, I draw a second sample. And on the basis of the combined results of the first sample and the second sample, I decide whether to accept the lot or to reject the lot. This is called double sampling. And if you generalize that, you can go to multiple sampling, or you could even go to sequential sampling. That you could do quite easily. Then there is another approach which is used sometimes combined with the single sampling plan. That is called rectified sampling. What we do there is I look at the rejected lots. I've got now a production system that is running, and it's dependent on the supplier's parts that have arrived, and I have to keep my production plan going. I've got to make sure that my production keeps going. I've received this lot. Unfortunately, the lot has been rejected by my acceptance sampling scheme. Perhaps I used a single sampling plan and I've rejected a particular lot. So I've got a full lot there. I've got a huge lot there that has been rejected because there are a few defective items there. So there are a few defective items in that lot there. What I do is I take this rejected lot. There are two possibilities here. One is I return this full lot, the rejected lot, to the supplier. I could do that. That's like one way. But that might stop my production. That might stop the supply of parts to my production shop. So this is something I perhaps would like to avoid. What I'd like to do is I subject the rejected lot to 100% inspection, and I remove all the defective items, and in place of that I substitute some good items, good parts, and I accept the lot. I pass it on to production. This way what I've done is I've kept my production system going, and I've also removed the defective items. I've removed the defective items from it. So what I've got with me is basically a 100% inspected lot that really does not have any defect at all. This is like one other way. This method for applying your acceptance sampling is called rectified sampling. I'm rectifying the defective lot that is there. So I've got now two different ways to summarize this. I can do my sampling based on attributes. These are quality attributes, quality characteristics that can be classified between as good or bad. This is like one way. When I'm looking at attributes, I do it I do inspection, of course, and I sort items out between good items and bad items, and I do that based on some quality characteristic that I really call an attribute of that particular item. On the other hand, I could basically measure some quality characteristic of the incoming items, and those would be the moment I am applying a measurement. The moment I am applying a measurement to the device, I am using some sort of a gauge and I am trying to measure the length or diameter or something. The moment I am trying to do that, I am looking at a variable characteristic. And sampling can be done both using what I called the attribute sampling basis and also the variable sampling basis. Both can be done. And how am I going to be doing my inspection? I could apply the single sampling approach. I could apply the double sampling approach. I could apply the multiple sampling approach or the sequential sampling approach. I'm going to give you some details on these. And also, I'm going to show you how to design these plans. Given your AQL, RQL, that is the acceptable quality level, rejection quality level, and the consumer's risk and the producer's risk, how do I combine all this information and come up with an acceptable acceptance sampling scheme, which could be a double sampling plan or a single sampling plan or perhaps a sequential sampling plan. We're going to discuss that as we move along in this lecture there. What are some of the advantages of the single sampling plan? Clearly, because the sample size is small, sample size is just one sample actually, it turns out to be less expensive. And I'm doing sampling only once, so it's less expensive. And there is less inspection involved. And it works with a single sample only, a single sample. That means I reach into the lot and I grab only one sample out of it. That's a single sample. It's very possible that I could also use double sampling, which is I use my first sample, then I reach back into the lot and I draw another sample. and then I look at the fate of the first sample, and I look at the fate of combine that with the fate of the second sample, find out how many defectives there are in the first sample and in the second sample, and then apply some decision rule which will tell me whether I should accept the full lot or should reject it. The single sampling plan comes up with a simple rule, either to accept the entire lot or to reject it. If lots are rejected, generally that provides some incentive for the supplier to come up with good parts, to come up with good supplies. What are some of the disadvantages of the single sampling plan? Now, I told you single sampling plan is based on a limited number of items that you pick from the lot. So therefore, there is some risk involved. There is the risk of accepting a lot of poor quality. It's very possible, because all I'm doing is I'm banking on the performance of this sample. As far as sentencing that full lot is concerned, I'm banking on the performance of the items in this sample only. It's also possible when I'm doing acceptance sampling, I might be rejecting lots which are really of acceptable quality. That's also possible. Again, because it's very possible that the samples that I picked, just because of randomness, it might have ended up with a defective item. Even if the sample size is small, it might have ended up with a item that is defective. And that's actually a bad news, and unfortunately this leads to perhaps unjustifiable rejection of the full lot. That's something I have to worry about. And also it's something that is either it's to be taken up by the consumer or by the marketing people. Someone has to study extensively the requirements of the customer. Basically, we have to determine these quantities, the AQL quantity, the RQL quantity, and of course we also have to figure out the risks that are acceptable to the consumer and to the supplier. Those different items also we have to figure out. So if you're trying to do acceptance sampling as opposed to 100% inspection, you have these advantages and also you have these disadvantages. How are you going to form the lot? Now I'll give you some examples how to form the lot. Basically, a lot is something that is considered to be homogeneous. All these items that have been submitted to me as a lot, if they came in a box of pens, they should have been produced together. Their quality should be more or less uniform, and they should have been produced by the same operator if possible, on the same machine from same raw material. Otherwise, if I just look at a few items out of this, it's very possible that these items have different characteristics from those that are left in the lot. So I'd like to make sure that the full lot has uniform characteristics. So if I look at a full lot, they should have homogeneous characteristic around. They may have some defects, but the percent of that defect would be the same whether I'm looking at the top of the lot, the middle of the lot, or the back end of the lot. It should be uniform. In fact, also it is said that if you take larger lots, they tend to be more representative of the overall quality. If you take small lots, they tend to reflect local conditions of production. That's why it's always preferred that you accept large lots for your supplies, and then of course you try to do acceptance sampling and you try to decide whether to accept the lot or to reject the lot. Also, sampling has to be done basically by randomizing. Let me see if I can work this. I have a vertical camera here, and it shows you these different items here. I cannot just, when I'm sampling from this lot, imagine that this is the lot. If I'm doing that, I cannot just go and take this item, then this item, and then this item, and form my lot, and form my sample. I can't do that. I basically have to pick the items that I pick for my little n, that is the sample that I'm drawing, by homogenizing this thing. And in fact, in this case, I'll probably have to mix everything. And in this case, if I'm going to be doing it 3 times, I look at the full lot, I close my eyes, look at my eyes are closed, and then I go to the table and I pick one item, put it away, and I go to the second item, put it away, and I go to the third item, I put it away. In fact, what I've done is I've done randomizing, And by doing that, I picked these 3 items that have been picked randomly from the slot that I have there. So these items that I picked there, these are now going to be an unbiased sample taken out of the lot. I've not really used any kind of bias there. And this is what I show when I show you this cube here. This cube is, let's say, the full lot that is there. It's the truck standing there and it's got layers of these boxes. And there is, of course, the back end of the truck, there is the front end of the truck. When I'm doing sampling, I've got to make sure that I randomize. Maybe I'll take this one, then I'll take this item there, then I'll go back and I'll take this item, then I'll take that item, then maybe some item over here. So in other words, what I've done is I've tried to take a representation of the full lot that is there. This is something that I'd like to be able to do. Unless I do this, there are these possibilities: sample from the front or sample from the top of the pile. These are some mistakes which are made sometimes when sampling is done. Also, it's very possible that I did not randomize. I did not close my eyes, and in fact I was looking at what I was picking from the table. That's not such a fair deal. And also, I do not stratify. What are strata? Strata are layered: the top layer, the middle layer, the bottom layer. They all should get equal chance to be picked when I pick this sample. When I pick this sample, these should have come from any of those strata in a randomized manner. That's really the idea of doing randomized sampling. Let's now get into our nuts and bolts of the single sampling plan. First of all, this is to be recognized as the most common and the easiest to plan and the one that is easiest to use, but certainly it's not very efficient in terms of the average number of items that you have to sample. Now this will become a little more clear when I get into this. So what I'm doing in my single sampling plan scheme, I'm drawing one sample of size little n. I'm drawing an item that is of size little n. That is just one sample I draw. It will consist of n different items. It must consist of these n different items. Then I have this control number that goes along with this n. This control number C is chosen very carefully. In fact, together the number n and the count C, these together, they guarantee the risk protection that the consumer has and also the supplier has. These two numbers, n and C, they together guarantee the risk that the consumer will be subjected to and also the producer will be subjected to. So these n and C, they are to be determined very, very carefully. You cannot arbitrarily, I cannot go to a lot and decide that I'll pick 2 items from here and my control limit is going to be 1 defective item. I can't do that, because that will give me an unknown amount of risk as far as the producer is concerned, consumer is concerned, and as far as the producer is concerned, it will be the same story. So I must use some sort of a plan, which is a systematic plan. And it's been worked out keeping in mind AQL, RQL, and the 2 risks, the consumer's risk and the producer's risk. So those 4 items, they have to be taken together: AQL, RQL, consumer's risk and producer's risk. Those 4 items together will determine this N and C. And let's see how we do that. What is the rule now? My lot size is big N, my sample size is little n, my control number is C, and the number of defective items that I find in that n items that I pick, little n items that I pick from the sample to be D. The rule for rejecting or accepting the lot is as follows: if this D is less than or equal to C, accept the lot. D is the number of defective items I found in this little n items. If this D is greater than C, reject the lot. That's the rule. So what is this plan doing? It is giving me a sample size, it is giving me a control number, and it says now you go ahead and inspect your sample, which has little n items, find the number of defectives. If the number of defective items is less than or equal to C, accept the lot. There is nothing wrong with it. You could go ahead and accept it. It will be fine. It will guarantee you the kind of protection that you want. And by chance, if this D exceeds C, you must reject the lot. Otherwise, you will not get the protection that you want. Now, this same thing I have drawn up as a flow chart here for you. I take a randomized sample of little n items from the large n items, which is the lot. Lot size is my big N and sample size is little n. Inspect all the items in the sample. Now, sample now consists of little n items. So, I inspect all the items in that sample. I'm not inspecting the full lot. In fact, the only items I'm inspecting are those that are inside the sample there. And let's say I found D defective items in that sample of size little n. Then I compare that D to this control number C. C corresponds to little n. C and n, they are tied together. They together provide us the risk protection that we want. If D is less than or equal to C, accept the lot. This lot is quite all right. But if this D exceeds C, I come down this way, I reject the lot. Then of course, I can either decide to return the lot to the supplier, or I may do 100% inspection, remove all the defective items from that lot there and accept it for production, for my use in my production. So the single sampling plan procedure, it goes as follows. Out of big N items, inspect them all, find out how many defectives you've got, compare the number of defectives you found to this control number C. If D is less than C, accept the lot. If D is greater than C, reject the lot. Then of course either you can return it or you could do rectifying inspection. And this is the total single sampling plan scheme. And the same thing is shown out here. What I've done here is I've given you an idea of the size of the lot, that is 10,000 items. Now these would be just too many to inspect. If you wanted to inspect all these N items, all these 10,000 items, they're just too many to inspect. But then I have looked at my AQL, I've looked at my RQL, and I've looked at my consumer's risk and I've looked at my producer's risk. And then I've applied a process, some analysis, some calculations I've done. And from those calculations, I've determined the size of the sample to be little n. And that in this case turns out to be little n is 89 items. That is in this little green box there. I sample exactly those parts, those items, and I inspect them 100%. And I compare the item to C equal to 2. So for corresponding to the 89 number there, I have this control number called 2. I compared the number of defectives I found to do to 2, to in fact this number 2. If D is less than 2, I will accept the lot. If D is greater than 2, I'll reject the lot. That's the single sampling procedure. Now let's try to take a look at those risks that I was talking about. I was talking about two types of risks. One is because I'm just drawing a few samples. I'm drawing a few samples out of the full lot that is there. And I'm not really attempting to do full 100% inspection of the full lot. I'm not doing that. I'm just randomly picking 2 or 3 items out of this. I pick little n items, and on the results of the inspection done on these little n items, I decide whether to accept the full lot or to reject it. When I'm doing that, it's very possible that otherwise I have a good lot. Now, what is a good lot? A good lot is of quality level that is near AQL. AQL is the acceptable quality level for the user. It's very possible that the overall quality level of the full lot is near AQL. Now, ideally speaking, I should not be rejecting any of these lots. Any of these lots which are at quality level that is near AQL. But what ends up happening, because I'm doing sampling, I'm just picking up some items from this, and using those sampled items, I do my inspection and I decide the fate of the full lot based on the results of the sample here. I might be rejecting a good lot. It's very possible that my sample by chance turned out to be a defective, and a bunch of defectives there in my sample, and I end up rejecting an otherwise good lot. Now, this is a loss to the supplier. This is the rejection of a good lot. and this is the supplier or the producer's risk. So if you look at my screen here, alpha is the producer's risk, which is the chance of committing a type 1 error, which means the probability of rejecting a good lot which has got an average quality which is near AQL. That's the producer's risk. And generally speaking, this is kept around 5% in industry. Then of course you've got the other type of error also possible, which we call type 2 error, which is like acceptance of a bad lot. If you accept a bad lot which is generally near your RQL level is certainly a pretty high level of defects. You know, there are high number of defectives in the when the overall lot quality is near RQL. You end up with a lot of defectives in that lot there. Those are the ones that should really be rejecting. But it's very possible, because you're only basically sampling, you're not doing 100% inspection of the lot, but you're doing just a sample. You're just drawing a sample, and based on those n items, little n items, you're deciding the fate of the full lot. It's very possible that you'll end up accepting a bad lot, a lot which has got quality level that is near what we call RQL level. RQL level is the rejection quality level. Now this is now a problem for the user. So this is what we call the consumer's risk, or beta. This is beta, or the consumer's risk, and in industry generally this is put around 10%. Now obviously there are businesses that use far more stringent standards. They use standards which are far smaller than 5%, and also sometimes they also use beta numbers which are far smaller than 10%. These are norms that are set by industry. If the company is very stringent, they of course would like to make sure that they do not accept any defective items, or mostly they should not be accepting any defective items, defective lots. In that case, they would like actually to reduce beta to a pretty low value. On the other hand, it's also very possible that a producer is very fussy and he does not want to see good lots returned to him. So he would like to work with a alpha number which is quite small. So in fact, these two notations, alpha and beta, they signify now the producer's risk and the consumer's risk. Then there is something that actually puts all of this in a picture. Remember now, what we are talking about is the probability of accepting a lot and the probability of rejecting a lot. Now I could take a piece of paper and I could show you exactly what those quantities are. Let's try to do this. I have the same picture that you have there. Let's try to work out the probability of accepting the lot. In this case, the probability of acceptance is going to be equal to my probability of finding C or less defects in the lot. Then there is a formula called the binomial distribution, which I am going to explain to you a little later. And that will be like this. This D will go from 0 to C, N D, P to the power D, and 1 minus P to the power N minus D. This is a little formula. Let me move this paper a little bit so you can see it all. This is the probability of accepting the lot. The probability of accepting the lot is, you are doing this when the number of defects you found, those are less than C. C is your control number. And that can happen if D is equal to 0 or D is equal to 1, 2, 3, 4 and so on up to C. And that probability is given by this binomial distribution. If the lot is of a large size, you can use this binomial distribution to evaluate this probability. This is the probability of acceptance. What is the probability of rejection? The probability of rejection, PR, is then going to be 1 minus PA. This is the probability of rejecting the lot. So probability of rejection is going to be 1 minus PA. This is the probability of your rejecting the lot. And in all of these things, we have assumed that the input quality is P. In all of these, we have assumed that the input quality is P. So, input quality is P. Given that input quality is P, this is the probability of accepting the lot, and this is the probability of rejecting the lot. These two are very, very important quantities, PR and PA. In fact, they determine how the overall sampling plan is going to work. And that will proceed, that will follow on with as we move into the later part of this lecture there. Thank you very much.